Now that we understand a little bit about the fretboard itself and a little bit about the concept of Western chromatic scale, we can now understand the fretboard a little bit better from the mathematical perspective. So again, Pythagoras decided that what sounded best to him, most pleasing to the ear, was known as the Western chromatic scale, or equal temperament. And the assumption behind equal temperament, once again, is that adjacent notes, if you're to fret a note and then play the note in the next fret, the frequencies of the notes should have a common ratio. So although the low E string has a frequency of about 82 hertz, we will just go ahead and in general just call that note, or the frequency of the open note, because it doesn't have to just be the E string, it could be the A string or the D string or whatever. We will just generically call that frequency of our first note, we'll call that F naught. Okay, and so then the next note in the, if you were to fret the first fret and play that note, that would be an F note, and then the F sharp, that would be here, and then a G, that would be playing here, and a G sharp, and so on and so forth. So each of these notes has a frequency. E to F, that will F sub 0 just means open. That means you're not fretting any of the frets. F1 just stands for the frequency of the note that you play in the first fret. F2 will be the frequency of the note you play in the second fret, and so on. Okay, and what we know from Pythagoras' assumption is that the ratio between any two frequencies is going to be common. So in other words, if we take the frequency of the note played on an open string, and we multiply it by this factor r. Again, I don't know what this number is, neither did Pythagoras, but he just said, that sounds, let's try that. And he would get the frequency of the note in the first fret. Similarly, if you take the frequency of the note played in the first fret and you multiply it by that same common ratio, or that same common factor, then you're going to get the frequency of the note in the second fret. You repeat this to get the note of the frequency of the note in the third fret. You would take the frequency of the note in the second fret and multiply it by this common ratio r. Well, how far does this thing go? Let's back up here a second. If we look at this Western chromatic scale circle, then these frequencies are they're going to be 12 of them, one for every single note around the circle. So let's just say we're starting with E, so that would be called F0, F1, F2, F3, F4, F5, and we keep going here. We should stop at F12, and that should give us the frequency of the note one octave later. Okay, so F12 will put us back here. Why aren't we calling that F sub 0 again? Well, because we've continuously around this circle from E back to E, we've made the frequencies higher and higher and higher. We are still playing an E note when we correspond the frequency to F12. However, the frequency is no longer the same as the frequency of F0, right? Because we're playing higher and higher notes. It's just eventually we produce the same sound as the note that we started with. Now, why is that important? Well, one octave, or an octave, is a doubling of frequency. So that's why if you hear, let's say, an a cappella group, and you hear the baritone, you hear the tenor, they can sing the same note, and you can tell that one's higher and one's lower, but they're playing one octave or maybe 2 or 3 octaves apart. So that allows me to establish a mathematical identity. This identity that we're going to use is that F12, the frequency of the note in the 12th fret, is going to be double the frequency of the open string. So we've basically traveled one full octave. We've gone from E to E. So that's a doubling of the frequency. Now, that in conjunction with what we have here so far, well, this seems kind of like it's going to be really, really messy because there are going to be so many subscripts of F. But notice something that we can do here mathematically is we can now begin to make some substitutions. So we know that F1 is equal to this common factor R times F sub 0. Well, if that's true, then anywhere I see an F1, I can replace it with R times F0, right? So F1 is equal to that, which means I can plug it in there. So that will give me R times R times F0 equals F2. That's nice because now I can express the frequency of the note in the second fret as a function of the frequency of the open note. And also I see that R times R is simply R squared, so the frequency of the note in the second fret is equal to R squared times the open note frequency. Down here I have the same substitution I can make. I know that F2 is equal to R times F1, which is R squared times F naught, so I can use this identity here now to say, well, in this equation I'm going to replace F2 with R squared times F0. So I will have R times F2, well, F2 is R squared times F0, and that will produce F3. So I'm making substitutions here and I'm just simplifying. And I have R times R squared, and R times R squared is R cubed, times F naught, so F3 is equal to R cubed times F naught. And we see a pattern emerging here. If I were to continue in this fashion, I notice that whatever note, whatever fret I'm in, the exponent on R will simply be that fret number. So what I can say in general is that F sub 12 is going to equal R to the 12th times F sub 0. Well, what I'm trying to do here is I want to solve for what should R be in order for this scale to work out right. Right now that's not so clear because I have three unknowns. I have F12, I have F naught, and I have R12. But one thing that I do know is that F12 from what we established in the previous slide is 2 times F0. That means that I can replace F12 with 2 times F0. And I want to do that because then I will have not 3 unknowns, but only 2 unknowns. Okay, so what I'm going to do here is I'm going to replace F12 with what it's equal to. So it's also equal to 2 times F0. And so 2 times F0 is equal to R to the 12th times F sub 0. Almost done. So now what I can do here is I can divide both sides through by F sub 0. Okay, so I'm going to do that in the next slide here. Actually, I'll just go ahead and do it. Start to wander here on the slide page. But if I divide both sides by F sub 0, I'll do that in a different color so you can see what's going on here. I'll divide both sides by F0. The reason I'm going to do that is because I see they're going to cancel out, and I'll be left with the equation 2 equals R to the 12th. Well, now I went from having 3 unknowns in the equation to only having 1 unknown, and I can solve for that. Now you have to kind of remember our algebra a little bit. How do we solve for R if it's raised to the 12th power? Well, it's the same question as how do you solve for x if you have 4 equals x squared? Well, you take the square root of both sides, and of course we put a plus or minus there, but we're only looking for R can't be a negative number, otherwise we get negative frequencies. So we would take the square root of both sides. Well, if it's the square root is really the second root of x squared. So if I have R to the 12th, I'm going to take the 12th root of both sides, and I'm left with R equals the 12th root of 2. Another way to write that would be 2 to the 1/12th power. That's 1/12th power is the same thing as the 12th root. And now I can compute this number, and the 12th root of 2, and I'm doing this in my calculator, comes out to about 1.06 roughly. 2 to the 1/12th, and my calculator here produces an estimate of, to about 4 decimal places, 1.0595. So the frequencies are all, if you think about this in terms of your knowledge of exponential functions, this is a growth factor of 1.0595, which means a growth rate of about 5.95%. So the frequencies from one fret to the next grow by about 5.95%. Therefore, if an E is 82 hertz, if I take 82 and multiply it by 1.0595, I get 86.879, or about 87 hertz. So that should be the frequency of the F note that I play next. Now if I take that number and I multiply it by 1.0595 in my calculator here, I get about 92 hertz for an F sharp. And if I multiply that by 1.0595, I get 98 hertz approximately. I'm rounding to the nearest whole number. Now, if I take 82, according to this equation here, if I take 82, my F naught, so I'm going to replace that with 82, and I multiply it by r to the 12th power. Well, that's going to be 1.0595 to the 12th power. What I should get is the frequency of the note played in the 12th fret. Now, we know by composition that that should equal doubling the frequency of the E note here. So this F12 note should be about 164 hertz. So let me do that in my calculator. 1.0595 raised to the 12th power, and I'm going to multiply that by 82, and I get to the nearest whole number, F12 is equal to 164 hertz. So we can see that the way we've set the problem up, I've ensured that playing an open string and then fretting a note at the 12th fret and playing it will result in a doubling of the frequency. And that is the most common, the most important mathematical relationship based on the Western chromatic scale. So what we know now about the Western chromatic scale is the frequency of any note in the Western chromatic scale is the 12th root of 2 times the frequency of the note just before it. So if I take a B note and take its frequency and I multiply it by the 12th root of 2, I will get the frequency of the C note. If I take the frequency of the C note and I multiply it by the 12th root of 2, I am going to get a C sharp, and so on and so forth. And if I take the frequency of the C note and I multiply it by the 12th root of 2 raised to the 12th power, then I'm going to get exactly a doubling in the frequency. You can see that if I take a frequency and I multiply it by the ratio, or that common factor, the 12th root of 2, that's r, raised to the 12th power. Well, if I take the 12th root of something and then I raise it to the 12th power, those operations cancel, and I will simply get a doubling of the frequency. The other thing that is valuable to note is there are really many C notes. That there's something we know as middle C. If you're a piano player, you might be more familiar with the idea of middle C. And this applies to D notes, E notes, etc. I'm just picking on the C note because that's kind of the most common or basic note or scale that we know of. And so I could play a C note, and the lowest perceptible C note is what we call C0. Okay, so that is like, it's below 20 hertz, but that's really the lowest sound, I think, C note that we can expect anybody to ever perceive. One octave later, you'd get the C1 note. One octave later, you get the C2 note, C3 note, and these are just doubling of frequencies. So if you took this guy's frequency and you doubled it, then you'd get a C1. And if you doubled that, so 4 times F naught, you'd get C2. And if you doubled that, you'd get 8 times F naught, that would give you C3. And C4 is what we call middle C, and C8 is essentially actually beyond the most perceptible C note. That's like beyond 20 kilohertz, but this is, C8 is actually well below 20 kilohertz, but anything above that just sounds very uncomfortable. Even the C8, if you go to a tone generator and generate a C8, which is around 4,500 hertz, it's a very, very, very high-pitched note. You start getting into the 10,000s, it starts to hurt your ear quite a bit. So that's an important thing to note, and so the C8 would be basically, 16, 32, 64, 128, 256 times this frequency. So if you think about this frequency here and you multiply it by 256, that will give you the eighth octave version of that same note. So we'll go ahead and stop there. The next thing we want to do is, in order to understand how this fretboard is fretted, we need to get into a tiny bit of the physics, or the physics assumptions behind how this works. And in the next video, we're actually going to establish the mathematical formula that will tell us where do we position those frets in order to get the Western chromatic scale. This math tells us how the notes should work out, but now we've got to physically apply it to a fretboard. See you in the next video.